Hello, welcome to the new chapter. In this chapter, we will be discussing time response of first order and second order systems. So far we started with some mathematical tool sets. Then we stepped into modeling of mechanical systems to build differential equations that describe the behavior of the system. And we are at a stage now that we have differential equations and we can start analyzing their response, how the behavior changes, what are the dependency of shape of the behavior on parameters, and dig a little deep into these time domain response. So here I have already written everything, not everything, many of the things. These are all only definitions that I thought are important to properly define and we can know what we are talking about. Let's begin by this differential equation. So this is a general form of an nth order differential equation, a linear one, linear time invariant. For now, doesn't really matter, but let's assume these a's are constant, and we have some input function p. So the first definition here is what we call the homogeneous equation. It's exactly the same differential equation, but written with zero input. So this is something from the differential equation course. So with this homogeneous equation and the full differential equation, let's define some terminology. The first set of terminology, this is one thing that shows up with different names in different contexts. In differential equation, we call it complementary solution. In system dynamics, either we call it zero input or natural response of the system. And all of these mean the same thing. They are the solution for this homogeneous equation. And essentially what it is the response of the system solely due to its own initial condition without any external input. So natural response, zero input response, and complementary solution are inherent behavior of the system without an existing external output, external input. Now coming to this side, maybe I can stand here. Similar to natural response, we have forced response, or in the differential equation, it's usually referred to as the particular solution, or zero state response. And all of them are the solution to this equation, but with the important note here that here we assume the initial condition is zero. So this forced response is the solution when we assume no initial state, the system is completely at rest, and it is driven by this forcing term. And all of these basically mean the same thing. If you remember from differential equation, the solution to a full differential equation is a combination of the two, and that's what we have. So essentially a system's response that is subject to both non-zero initial condition and some input can be constructed by summing up the forced response and natural response. And this comes naturally as the linear property of this differential equation. This would not hold for nonlinear differential equations. All right, so these are some terminologies. Another two piece of terminology that we will come to it often is steady state response and transient response. It is easier to think about a steady state first. A steady state is essentially any behavior that doesn't change with time as time goes to infinity. So in long time horizons, the system remains quote unquote stable. That is not the technical definition of a stable, but a colloquial stable. Opposite to that, we have transient response, and transient response is any varying response until we arrive at the steady state response. So anything before steady state, we consider it transient. And I have two examples of two kinds of steady state. So if imagine you have a system whose response is going up and down until it settles to a constant value. After it reaches that constant value, this is our steady state regime, and anything before that is transient, or the transient phase of the response. There is a little bit of confusion. It is also possible to have a varying response and have a steady state. And I have just this cartoon example of a sinusoid whose amplitude increases, and after a while the characteristics of the response, the shape, the frequency and amplitude of it does not change after some point, and that is also something we call steady state. And obviously before that, when we have these changes in amplitude, frequency, or shape of the response, we call it transient. And just a little bit of theoretical note. A system has a steady state response only if its natural response goes to zero. It's a way to say that the effects of the behavior, effects of the initial condition die out over time. And also for that, for a steady state to exist, we need to have the forcing term somehow causing a bounded response. So if the forcing term causes the system to blow up, we will not have a steady state. So these are all definitions, and it is, although I just went over them relatively quickly, I think it is worthwhile if you pause the video and think about them, try to internalize them, think what they mean until I clean the board and we come back and continue. All right, so now let's take a look at our first kind of system, the first order linear time invariant system. This is a generic form that you can describe any first order linear time invariant system with such a differential equation. A constant multiplied by x dot. This is an easy way to work with, an easy form. There are many examples of this system. For instance, a RC, resistance and capacitor system, a massless system with a spring and a damper, or a pressurized chamber that releases into some outside pressure P, and many others. So what is common among all these systems is that you have a variable x, and in all of this system, the rate of change of that variable depends on its current value. If I want to rewrite this, so it's going to be x dot equals minus 1 over tau x, possibly there is some input too. So the rate of change depends on the current value. This is the most important aspect of these simple systems. And it really doesn't matter what physical or non-physical system does this equation represent. All of them share the same characteristic behavior that we will see. So as long as you can represent your system through that, you know how the system's response will look like. So all right, let's Let's start by analyzing the time response of the system. The first thing we can do is to look at the natural response. Also means the response of the system when there is no input and we have some non-zero initial condition. So in this case, the differential equation will be tau x dot plus x equals 0. I only have a first order system, so I only need to know the initial condition of x. Let's, for simplicity, call it x naught. This system is easy enough, so we can solve it using Laplace. So if you remember this, taking Laplace of this whole equation, I have tau s x of s minus x naught plus x of s equals 0. And I can rearrange and do some reorganization. I have tau s plus 1. I take this to the other side and divide, so x of s becomes x naught over tau s plus 1. I'm missing a tau. Here. Tau x naught. Let me be a little neat. Cleanliness, that's what matters. Tau x naught. And I can factor out one tau to make it a little nicer. So it's going to be, I'm going to write it like that. X naught 1 over s plus 1 over tau. And this is one of the most basic forms for a Laplace of a function. If you look up the table or think about it, its equivalent time domain function is x naught e to the minus 1 over tau t. So that is my differential equation, my solution to the differential equation. And all of these systems will have a natural response that look like that. Doesn't matter the form, this is the solution. And this is a very nice, interesting characteristic form. If you want to plot that, so I'm plotting x of t versus time. The way it looks like is something like this. It's an exponential decay, and let's take a moment and think about this tau. Tau here is a very characteristic term. Tau is called the time constant. Time constant of this system. So for this one, if I recall correctly, that's r times c. For this one is, I think, k over b, b over k. That's b over k. For this one, I don't know, I don't remember. It must be related to the resistance of this valve and something else. I don't know. Pneumatic is not my field. All right. So what does this time constant really mean? In this characteristic form, and by the way, this starts from the initial value x naught. It is very handy to know. So if this is my original x naught level, So at every time constant, I keep writing it with red. This is tau, 2 tau, 3 tau, 4 tau, oh, that's pi, 5 tau, and so on. So as soon as one time constant has passed, well, my figure is not very characteristic, but that's fine. We lose 63.2%. So immediately one time constant after the response begins, the value drops to 62% of what it was before. No, not 62% of what it was before. It loses 62% of its original value. After two time constant, it drops 86.5%. After three time constants, 95%. After four time constant, 98.2. And essentially by the time you have passed 5 times the time constant of the system, you are at 0. So you have lost 99.3% of your original value. And this doesn't matter where x naught is, how large x naught is, and how slow or fast the system is. As long as you know you can define the time constant as this tau in that form, you already know how the response will look like. And it is noteworthy to remember this has unit of time. So we have b over k. This has unit of second. RC has unit of second. So all of these have the dimensions of time, and they define our characteristic time constant. So that is the response of the system only due to its initial condition. The next thing we can do is to look at the forced response. So in forced response, we take the initial condition to be 0. Instead, we have some forcing term. So I will have tau x dot plus x equals some p of tau, some input, with the initial condition of x of 0 equals 0. So let me again take the Laplace transform. I have tau x of s, because this one is 0. Oops, I'm missing an s. Tau s x of s. This one is 0, so it disappears, plus x of s equals p of s. Both of them are capital, but I have taken Laplace transform. And from here, x of s is p of s over tau s plus 1. So before I continue, you can see the difference. So this natural response was created because we had this initial condition, and the forced response is because we have this forcing term. So something interesting to keep in mind, where these dissociate or separation of the force and natural response comes in, and later when we add them together, where they come from. So this response obviously depends on what P of S is. But before that, we should already expect to see exponential. Because if you remember, the poles or the S values where the denominator is 0 defines the characteristics or the modes of the response. And it still has the root of minus 1 over tau. So I'm expecting to see something like that. But the particular shape of it depends on P. And it can change based on what the input is. So one of the most useful information we can get is something called a step response. And that is when this P of t is a step. So it looks something like that. 0 jumps to 1. P of t. Maybe if I want to make it nicer, let's give it some amplitude A2. So P comes from 0, jumps at A, and remains at A. This is A. And Laplace transform of this step is P of S is A over S. So knowing this, substituting that here, my x of s becomes A over tau. I'm going to factor out a tau, 1 divided by s plus 1 over tau. And this can be written as, if you do the separation, maybe I didn't need to do this, I don't know. So it's going to be A times 1 over S minus 1 over S minus 1 over tau plus tau. So if you do the manipulation, it will work out. On the top we have S plus 1 over tau minus S, so it's 1 over tau comes here, we have that. And taking Laplace inverse of that, x of t is a constant value, 1 over S is 1 minus e to the minus t over tau. That's a little too big. And as expected, this characteristic form showed up, but now it is kind of modified by the presence of the inputs. And how this response looks like, x of t versus time. So at t equals 0, we have 1 minus e to the power 0, and that is 0. So I start from here as expected, because my original initial condition was 0. And as t goes to infinity, assuming that tau is a positive value, it's e to the minus some large number, so that one goes to 0, and I'll converge to a. I will reach to somewhere that a, and the rate of increase is exponential. So I'll try to make it something like that. And comparing these two, essentially this one is flipped and maybe scaled. Instead of having the height x naught. Now it is reaching to A, and the same argument holds. So after after the time passes a few time constants, 3t, 4t, 5t, I will rise with the same proportions. So I'll rise 63% to the maximum value. I rise 86%, 95, 98, and 99. Oops. So this exponential growth, not exponential growth, exponential convergence to a constant value and exponential decay to zero are the characteristic behavior of this first order systems that have a time constant tau. Alright, so we started by looking at the natural response due to initial condition, and then looked at force response. One particular example of that, when we have step response, the input is a step, and we see this. So let me clean up the board. We can continue with one more condition, and that should be it for this class. Okay, so let's look at another example of this first order system when the input is a ramp function. So the input is assumed to be 0 and then increases with some slope r with time. So writing the first order differential equation again here, we can take the Laplace transform. I have tau x of s plus tau s x of s plus x of s equals this one has a Laplace transform of t. This ramp is 1 over s squared multiplied by the constant rate r over s squared, and taking x of s is going to be r 1 over s squared 1 over tau s plus 1, which I can write it as r 1 over s squared minus tau over s plus tau over s plus 1 over tau. And this one has the corresponding time domain function of r. So this is going to be a t. This one is 1, and that one is an exponential function. So I'll have r times t minus tau. These are the first two terms, plus r tau e to the minus t over tau. And again, you see this characteristic shape showed up regardless of the input. But now, because of input having other poles, we have new terms or new shapes of the response. And let me plot that here. If we plot the response as a function of time, this is x of t. I start at 0. Let me first plot the input. So this is my input. I can do this. This is the input, a line with some slope r. What this response does is, think of it this way. So originally, I have some value that is, well, look at this one first. It is a function that is parallel to, it's the same slope, RT, but it has a negative y-intercept, so it's something like this. And this distance is r tau. But because of this exponential term, it starts at 0, and then the effects of exponential dies out, and my function reaches out this tangent line. So at any time, I'm lagging some RT behind the input. And this lag is, you can think about it using perhaps a spring damper system of this type. So if I apply a force and I keep increasing my force, well, maybe not this is not the best mechanical thing to think about. Think of it this way. I have a spring attached to a damper. Now I start to pull this. This system also has the same equation, but instead of force, this one is a position. So if I start to pull this point, because of the existence of the damper, it starts to lag behind and follow me, but with a certain lag. And that is what this distance is about. And one other thing to think about is if you take the difference of these two, so let me call it E, error or difference, of x minus p, the RT cancels. I will have maybe p minus x. That's nicer. Let's do p minus x. P minus x. So the RT cancels. I will have tau minus e to the minus t over tau. And this, I have erased it, but this is exactly the same shape as the step response. That my error starts at 0, but eventually starts to lag behind until it reaches this steady state error of, I'm missing an R, R tau. So this is error as a function of time. That's what we are plotting. Okay, these are two characteristic, not characteristic, kind of famous, important responses of the first order system that we kind of should know and internalize it by heart. So whenever you see an equation of the form tau x dot plus x, you should know it's an exponential convergence to something, either coming to 0 in terms of a natural response or exponentially approaching an input value if it is a step response, or if it's a ramp, exponentially converging to a steady state error, and follow the input with that. Okay, that is that. And the last bit that can be important to know is we studied natural response, we studied forced response, and the last thing maybe important to know is to talk about full response, which is the summation of natural and forced responses. And if I want to write it, tau x dot plus x equals some pt with non-zero initial condition of x of t equals 0, x naught. So this will have tau, we wrote it before, s x of s. I have to do this. X of s minus x naught plus x of s equals p of s. And rearranging things, I will arrive at x of s equals p of s divided by tau s plus 1 plus x naught divided by tau s plus 1. I need a tau here too. So, and these two are precisely what we have up here. This one is natural response, and this one is forced response. And this form doesn't matter if we have a first order or second order or any other order system, as long as we have a linear differential equation. Linear, I think time invariant differential equation. I'm not sure about time variant part. Maybe even time variant. This will always hold. That the full response is the summation of the forced response due to the forcing term plus the natural response due to the initial conditions. All right, that wraps up the first order system time domain analysis of first order systems. So in the next lecture, we step up the order. We look at the second order systems. And in future lectures, instead of time domain analysis, we can also look at frequency domain analysis. So until then, happy studying.